So let us continue from the last video. In the last video, I talk about what are the assumptions that we need to check when we do the hypothesis testing for the linear regression. Okay, and we were talking. So first of all, we'll talk about the simple linear regression, meaning that there will be only one independent variable, and later we'll talk about the multiple linear regression, meaning that there will be more than one independent variable. Okay. So in the regression line, y hat equals to a plus bx, the slope b expresses the straight line dependence on y on x, of y on x in the sample. Okay, it does not necessarily mean that there is a dependence in the population, because this just tells about the sample only, whether the sample x values causing the sample y values or not, causing changes in the sample y values or not. If there is, then the changes will be beta per unit x change. Okay, sorry, b per unit x change. But we want to know what will happen in the population. So it does not necessarily mean that there is a dependence on the population. That means that if b is not equals to 0, what that means? That means for every unit change in x, you will see b unit change in y. But if b is 0, you see that for any change in x, there is no change in y, because y will be a all the time if b is 0, right? That is for the sample. Now, using that sample correlation coefficient, you want to test hypothesis for the population, for sample regression coefficient. I'm sorry. So, to test if there is a regression between x and y, because you know the difference between regression and correlation, right? So correlation does not care the cause and effect, right? It's just if you find the correlation between x and y or y and x, you will get the same answer, same correlation coefficient. Okay, but the regression is there is one dependent variable, other is independent variable. Dependent variable is y, independent variable is x, and you find out the slope b for the sample. That means for every one unit change, for every one change in x values, there will be b unit change in y value. Okay, if b is 0, meaning that y hat will be all the time a, that means that there is no change in y if b is 0. Similarly, in the population, if beta is 0, then there will be no change in y. Okay, now just in other hypothesis testing, we want to assess how likely is it to obtain a sample with non-zero slope from a population with 0 slope. Okay, that's what we will be testing here, because if you get non-zero slope in the sample, can we generalize that in the population? Can we say that there is non-zero slope in the population or not? Okay, thus our null hypothesis and the alternative hypothesis will be H0 is beta is equals to 0, meaning the population slope is 0 versus beta not equals to 0. That is the alternative hypothesis. Beta is the population, right? To find out the test value, the second step will be the test value or the test statistic. We need the following: total sum of square. What is the total sum of square? It's summation of yi minus y bar square. That means yi are the data. So you find out the mean of the whole y data values, and you do y each data minus the mean square, and you add all those sum of squares. You add all those squares of the deviations, right? That is the deviation from the data, and the square and then sum. The degrees of freedom will be n minus 1, where n is the number of pairs. Okay, next is the regression SS. So to find out the regression SS, you do the same thing, but not from the data, but from the predicted value for each y, or for each x you predict y using the linear equation. Okay, and you find out that difference of those predicted value minus the mean of the y values there. Okay, and then square. So it is the deviation from the predicted. The degrees of freedom is k. What is that? K means number of independent variables. Okay, so k is the number of independent variables. So in case of the simple linear regression, it will be just 1, because there will be just one x and one y, so just one x. That means only one independent variable. If there are multiple linear regression, we will have multiple independent variables, 2, 3 independent variables. At that time, the value of k will be different from 1. Okay, and the residual SS is the difference. This is the error square, sum of the error square. That's the residual SS, meaning you find out the difference of the data from the line. This is the predicted value from the line, right? Data minus the line square. This is one way. Another way is total SS minus regression SS. You find out this and then minus, you find out that. Also give you the same value. Okay, the degrees of freedom will be n minus k minus 1. So if it is a simple linear regression, meaning that if there is only one x variable, then k will be 1, so it will be n minus 2 will be the degrees of freedom. Okay, first of all you need to find out these, and then where k is the number of independent variables. Also to find out the corresponding mean square error. So we need to find out, first of all you need to find out these three, and you find out the mean square error as we did in the ANOVA. Okay, so for the mean square error you need to divide the total sum of square as total SS by degrees of freedom, regression SS by degrees of freedom, residual SS by degrees of freedom, and you find out the mean square. So mean square regression SS will be this value whatever you get and divide by k. Mean square residual will be the whatever you get here and then divide by n minus k minus 1. Okay, and you find out the f, the test value. The actual test value will be regression MS over residual MS, mean square. Okay, the test is always the right tail. We always use the right tail test, and p value will be 1 minus pf, just 1f. Okay, not 2f. pf and then parenthesis k f value. Oh, I'm missing the parenthesis here. I'm missing the parenthesis. Okay, guys. So I will correct that in the lecture notes, in lecture slide. So p value is 1 minus pf and then parenthesis f k and then n minus k minus 1. If p is less than alpha, we reject the H0. Okay, so so the residual mean square is often written as s square y x. Okay, it's square of s y x is called the standard error of estimate. So you see the residual mean square. So residual mean square, that value is what? The residual SS over, residual mean square is the denominator here, right? Which is given by residual SS divided by n minus k minus 1. The notation for this is s square y dot x. S square and sum y dot x. Its square root is syx, is called the standard error of estimate. That's what we call the square root of the residual mean square. This quantity is an indication of the accuracy with which the fitted regression function predicts the dependence of y and x. And another thing we use is coefficient of determination. The ratio of regression SS and the total SS. You see that? Ratio of the regression SS divided by the total SS. Okay? Is called the coefficient of determination. And this is the exactly same as the R square. What is the R? Do you remember the correlation coefficient? If you find the correlation coefficient that way, the way that we did in the last slides, and then you do this way, regression divided by the total, you get the same value. Okay, R square is often used as a measure of strength of the straight line relationship. It is sometimes referred to as expressing the goodness of fit of the line to the data as the precision of the regression. So usually what you get is whenever we do we use R to do the regression test, hypothesis testing for the regression, you will automatically see the value of R square. So R square is basically used to say what is the strength of the fitting of the data and the predicted line. Okay, so usually if R square is greater than 0.8, we say that is a good fitting. If the R square is smaller values, close to 0, we say that the fitting is not good. Okay, that's what we interpret that way. Okay, let us see an example. So the following data is the wing length of the sample of 13 sparrows of various ages. Find the regression line. First of all, you need to write y equals to a plus bx for alpha equals 0.05 and for alpha equals 0.05, test the dependence of wing length on age. Okay, if the wing length depends on age or not, meaning that if the increase or decrease in the age causes the increase and decrease of the wing length or not. That's what we are going to test here. Okay, So here the regression line, you find out the regression line, you do the linear model, you get the regression line. Okay, let us do that. I have copied that X data and the age and Y data as the length. Let me run that. If you look at the plot, how would that look like, the scatter plot? This is what the scatter plot look like. It sounds good plot, right? You see that? Because if you look at the if you look at the dots here or the data here, they look like along the straight line, right? So I denoted the model 2 because previously I denoted by model 1. No worries. But the main thing is the right side. So LM, first write down Y and then wiggle sign and then X. That's what you do, okay? Because we want to see if the length is depending on the age or not. So model 2, we got the age is 0.27. That is the regression coefficient. That is the value of B. And the intercept is, that is the value of A. You see that? Y hat equals to A plus BX. That's what we got. A plus BX. Now, this is for the sample though. This is for the sample data. You see that the value of B is not 0. But how about the population? Is the population regression coefficient, that is the beta value, is 0 or non-zero? Is it significantly different from 0 or not? That's what you want to see. Okay. So H0 is beta equals to 0. That means no linear dependency of wing length on age, and H1 is beta not equal to 0, meaning actually wing length depend on the age. That's what we are saying here. Okay. So what is the test value? To find out the test value, first of all, I am going to show you how to find the test value using manually, okay? And then I will show you how to do the whole hypothesis testing using R directly. So I'm going to do that manually first, and then directly from R later. Okay. So for the test value, first of all, n is equals to 13. What is the total sum of square? Total sum of square is, you find out the difference of each data from each Y data. Difference of each Y data, this Y data, right? These are the Y data. First of all, you find out the mean of those Y data, and then find the difference of these, each of those Y data from the mean, and square them, square the deviation. So square of the deviations of the data from the mean, okay, and then you add them together. That is the sum. Okay. So what I'm doing here is, let me see here. So n is the length of the age or length of the length. That uppercase length is the name of that data set, right? This lowercase length is counts how many are there. So n, first of all, find out n, and then what is k? K is the number of independent variable. Number of x, this is x variable here, right? There is only one x variable, so that is k is 1 here. So k is 1. Now total sum of square is sum of length is the y value. That's y, right? Length minus mean of the y. So y minus mean of y square, and then you add them. That's what the formula says, right? You see that? Yi is the data minus the mean of those data, square, and then add that summation. That's what you do. If you do that, you get total sum of square is 19.656923. You see that? Okay. Next is, you want to find out the predicted value. You see that? What is the regression assessments? The predicted y values minus the mean of the data, square, and then add them, sum of that. So to find out the predicted y values, first of all, what you need to do is y, the predicted y hat, basically, this is y hat, is this 0.7131, that's what we got, right? Y hat is plus 0.270x, 02x, because I consider 4 decimal places here, times the age. What is age? Age is that. That will give you the predicted value, right? If you run this is the y values you get. These are the y predicted values. Okay, guys? So these are the y data values, and these are the y predicted value. You see that? These are the y predicted value. Now you need to do y predicted value minus the mean of the data value, data y value, square, and then, so this is what I'm doing. Regression SS equals to sum of y, is that y, predicted y, minus mean of the length, square, and then if you add that, so how would that look like? Regression SS, let me do that. Regression SS would be, let me do that. So regression SS would be 19.128111. So that will be the regression SS, 19.128111. Okay. What is the degrees of freedom? Degrees of freedom is K. You see that? Degrees of freedom is K. So if you divide the regression SS by degrees of freedom, we denote that by regression MS, mean square. Okay. Regression MS is this divided by the degrees of freedom. We got the same value, right? Similarly for the residuals, what is the formula for residuals? Is yi minus y hat, meaning the data yi minus the predicted yi. Okay, you see that? That is one way to do that. The other way is, by the way, let me run those two as well, because the regression MS, right? Regression MS is regression SS divided by K, and residual SS. There are two ways. One way is total SS minus regression SS. Another way is you can do this way: the data minus the predicted square. You can do either way. You will get the same value. Okay, if you do that, then this is the residual SS. Let me see how much you get the value. So the residual SS will be 0.5288. Okay, so let me see, 0.5245. It's just the decimal places, how many decimal you considered. Okay, so that will be that value, 0.5288. That's what I got here. I put slightly different because I think I used calculator to do that when I did this, and then I considered only few decimal places. I think that is the reason. Okay, and the degrees of freedom is 11. Now we need to find out the residual MS is residual SS divided by the degrees of freedom. That's what you get, and residual MS is 0.4807. 0.04807. That is the residual MS. Now what is the F statistic, or the test value? Is residual MS over, regression MS over residual MS. You see that? 19.12811 over 0.0. So if you do that, then you get 397.8877. That's what I did here. So the F value is, let's say, 397.8877. This is the F value. Okay. So now to find out the P value, there are two ways. Okay, you can do the critical value method, or you can do the p-value method. So if you want to do the critical value method, you need to use the F table. F alpha is 0.05, right? It should be a right tail. That's why I wrote 1. So you need to do the right tail F test, K, and then n minus K minus 1. If you do that, you will get 4.84. So does it fall in the, does the test value fall in the rejection region? Yes, because this F test statistic fall in the rejection region because it's the right tail test, right? Anything right of this test critical value will fall in the critical region. Hence we reject the null hypothesis. Okay, so look at, if you find the p-value, it will be very small. I am showing here. Hence there are enough evidence that the wing length of sparrows depend on their edges. So if you find out the p-value, you get 1 minus pf, because we are finding the area right of the F test statistic there. 1 minus pf, f is that value, and then k is equals to 1, right? And then n minus k minus 1 is 11, right? If you do that, you will get that thing. Okay, I have done it here. That is the p-value, and then p-value we got 5.4982 times 10 to the negative 10. You see that? 10 to the e to the negative 10 means here it is 10 to the negative 10. Now, so I will show you how we find out SYX, which is the square root of the, so SYX, do you remember that we mentioned that residual mean square, the square of the residual mean square means square of residual mean square, that square root of that, you will get what? SYX, that is 2.218. That's what you get. And R square, if you find out the correlation coefficient, then you will get 0.97, which indicates the strong linear dependence of the wing. So we will see, okay, because when you use directly R, then it will list all those values also. Okay, so that's what we got. So p-value less than alpha, we can write here or later. Let's write later together. Okay, so you see that. So I want to do it directly. What I did, model 2, I did exactly same thing before. Model 2 here, right here, right? Model 2, and then linear model, length is the y value and the wiggle sign, and then x value is the age. You run this one, and then just write that model 2 will give you just x value, the coefficient, regression coefficient of the sample, and the y-intercept, right? And if you do the summary of model 2 like that, and it will give you everything that you need. Look at that. What are the x value? See the a and b value. This is a, this is b. The main thing we look at here is, you see that, so the intercept is 0.71309, and then age is the b value. This is a value, this is b value, and then another thing is the p value of the age. So this is significant. P value is less than alpha, right? So we reject the null hypothesis. Also, residual standard error, that is SYX. Okay, residual standard error is SYX is 218. 11 degrees of freedom for the residual mini square, right? Residual sum of square. Multiple R square, that is R square value, you get 0.97. You see that? Adjusted R square is also 0.97. And the test value is 401.1. I think it is because of the decimal places. No worries about that, okay? Also, the p value is that value we got. You see that? That's the same p value we got. So it is significant, meaning that beta is not equals to 0. We reject the null hypothesis, meaning that beta is not equals to 0. Okay, you see that indicates the strong linear dependence of wings length in AJ. That's what we got. Okay, so let us look at the note. You can do the above example using t-test. So there is another way to using the t-test. This method is more useful if you are testing one tail test, because this method, the F test method, uses for the two tail, but if you have to use the one tail test, which is less common, that's why I didn't show an example on this. In that case, it is easier to use t-test. I think it is showing the t value as well there. Okay, guys, and the t critical values there, or the t value there, the test value when you use the t-test. This method is more useful if you are testing one tail test. Also, if you are testing beta equals to 0 versus beta not equals to 0 is here, but if you have like some number, then the t-test method is more useful. In the t-test method, the null and alternative hypothesis of this problem actually is beta equals to beta 0 versus not equals 0, greater than 0, or less than beta 0. Okay, and the critical value is use t-table, and then n minus 2 degrees of freedom, and depending on less or greater, you find out those critical values, right? And to find out the test statistic, you do b minus beta 0 over sb, where beta 0 is that right side of the null hypothesis, b is the sample regression coefficient, and s sub b is the you find s square yx divided by summation x minus x bar square. That's what the formula you use, where x bar is the mean of the x. Okay, s square yx is the residual square, right? That's what we said, right? Residual mini square. That's what the residual mini square on the top. Okay, and if we do that for the above example, you get SB equals to 0.0135, T equals to 20, and T 0.5, 2 and 11. That is the critical value is 2.201, and you reject the null hypothesis. That's the same method. Okay, but if you want to find out the confidence interval, regression coefficient by hand, this is the formula you will be using, but we will be using R. Okay, we use R to find out the 95% confidence interval for both for A and B. I'll show you that one as well. Okay, so we did that, and then I draw the, if you want to draw the AV line, see that's the AV line here. You see that most of those data are along the line. You see that, what is the LWD stands for? LWD is basically the line width. It's the fat thick line here, right? Okay, now 95% confidence interval and the prediction interval. So prediction interval, you got, that's the prediction interval for y values. Okay, that's the fit and the prediction interval. But for confidence interval, it gives you the beta values. So prediction interval is for, the prediction interval is basically the confidence interval for the fitted y values, right? From your model, you find out the y values for each x values. That y values also has a confidence interval. That is called prediction interval. Okay, but if you want to find out the confidence interval for A and B, okay, or alpha and beta, that is better to say alpha and beta, this is what you do, conf int and model 2. That's what the model 2 is, right? If you run that, it will give you the 95% confidence interval. This is for x, the age or the x value, the beta. Okay, this is for the coefficient of x or beta. This is the confidence interval for beta. This is the confidence interval for population. It says 2.5 and 97.5. These are the percentile, right? So the middle part is basically the 95%, right? That's what you do. Okay, guys. So this is all about doing the simple linear regression test. Okay, analysis of the simple linear regression. Look at this. I think I had that already, so I don't need to run that. Let me show you something here. I have written the analysis result here. Let me look at this. Residuals provide the quick view of the error. Basically, what it is saying is the residual errors. Look at here. Residual standard error. Residual standard error provide the quick view of the error between the data and model. The residual always has mean 0. The residual has mean 0. Residual, oh, by the way, let me know, you don't need that. I have mentioned it here. Residual standard error RSE close to 0 indicates better fitting. Our RSE is 0.21, right? It is close to 0. R-squared and adjusted R-squared provide the percentage contribution in the variation of outcome variables that can be explained by the independent variable. So how well the data fits, the strength, okay? High value of R-square and R-square adjusted is the indication of good model. Usually the value greater than 0.7. Some people say greater than 0.8. Some people say 0.7, greater than 0.7 considered good, okay? So the next thing we want to do is the test of assumptions of the regression analysis. So let me see if I have an example there. Regression diagnostic test. Linear model. I think I have given an outside example here. I just wanted to see if I have an example that is different. Okay. That is the same as the example that we did. That's what I wanted to see. It sounds like no. So I have given another example here. I will show you how to use the regression analysis using R directly, and then how to test the assumptions. Okay. Let me see here. So faithful is a data. Okay. What is the faithful data? Okay, that's the faithful data. Okay. So what we want to see is, what is the faithful data? Let me run that faithful data here. Okay. So this is the faithful data. What it is doing here. Oh, by the way, it's a big data set. So you can check what is the faithful data stands for. It says waiting time between eruptions and the duration of the eruption for an old faithful geyser in Yellowstone National Park. Okay. They actually recorded the waiting time and the eruption time. Okay. The first column here is the eruption time and then waiting time. Okay. Look at this. So faithful, the first is eruption time in minutes, and then another is the waiting time in minutes. Okay. So these are the eruption times, like 3.6. So it erupt 3.6 minutes, and then the first time they recorded, it erupted 3.6 minutes, and then it stopped for 79 minutes, and it erupted again, like that. And another they recorded 1.8 minutes, it erupted, and then 54 was the waiting time, and so on. That's what this data is. Okay. Now let us plot. How does the plot look like? This is what the plot look like. You see that? Looks like it goes to close to a line, right? But it has like some kind of more dense. You see that? More close, this data here and here, not in the middle. You see that? So let us find out the summary here. So we did the linear model. Eruption is the Y, okay, and waiting is the X. Data is the faithful. So what we did here is they are trying to see if the eruption time depends on the waiting time, meaning that if the longer waiting time results the longer eruption time or not. That's what they are going to test. We are going to test here. Okay. So when I do that, what did you get here? the intercept, what is the linear, the line, what is the equation of line is y equals negative 1.87 plus 0.075 times x. Okay, what is the p-value? P-value is, you see that p-value is less than alpha. So that means beta is significantly different from 0, because h0 will be beta equals to 0 and h1 will be beta not equals to 0. Since the p-value is less than 0, so beta is not equals to 0. Okay, residual standard error is 0.49. It is small. Okay, and R-square is 0.81, so it is also fitting well. Okay, 0.81. So we discussed that already, these things. Okay, now, so what is p-value? P-value is less than alpha, right? So p-value is less than alpha. So let me write down that. So p is less than alpha. So reject h0. So what does that mean? That means we'll have to test the assumptions later. We'll do that. Okay, if the assumption is violated, then we'll have to we will not conclude this way. But for now, until we check the assumptions, that's what we are going to do. I am writing that hence the eruption time depends linearly on waiting time. So that's what we can say from here. Okay, also as we mentioned, R-square value is bigger, so we are good. Bigger than 0.7 we are good, and then the RS is small, which is also good. P-value is less than alpha, so we rejected the null hypothesis. Okay, you see that if you want to draw the line, then this is the linear model. That's what we named it, right? What you can do is, this is the line, right? Because y equals to a plus bx, that's what you get. And then if you do the AV line here, that's what the AV line looks like. It is going to almost most of the points. It is going through the middle of the most of the points. Okay, now we want to test the assumption. Assumption is the first is the linearity of relations. How do I do that? The graphical method is plot linear model and then comma 1. That's the linearity of the relations. So how does the plot look like? Oh, by the way, let me do that, and then plot. Oops, why it's not plotting? Let me erase everything and then plot again. So linear model. Okay, let me run this linear model here. That's what we got. And then I am doing the linear model 1. This is what you see. You see that? So this red line is almost close to the dotted gray line, right? Or you can say that if it is not linear, then you see that red line will be like slightly increasing or slightly decreasing. It is not following a pattern, right? So we are okay. So look at this. Linearity of the relation, what I mentioned here. The relationship between x and y variable must be linear. It is checked by residual versus fitted plot. That's a residual versus fitted plot. This plot also checks homoscedasticity too. That is, you see that does it spread more in one side and less in the other side or not. Okay. A horizontal line without distinct pattern is an indication of linear relationship. The numbers in the plot is the rank of the data that is an outlier. Okay, you see that? There are some numbers, they are the outliers. Alright. So assumption 2 is the linearity of residuals. So this is what you check, plot linearity of residuals there. So it looks like it is linear, right? You see that? It is almost on the line. So you can do QQ line as well, but QQ plot showing that almost on the dotted line. Okay. Next is the homoscedasticity, homogeneity of variance. Let me talk about the assumption 2 again. So normality of residuals. Oh, I think we did that already, right? So for fixed value of x and y must be for fixed value of x, y must be normally distributed. To check the QQ plot for the residuals, so to check this, we run the QQ plot for the residuals. We did plot linear model 2. Examine whether the residuals are normally distributed. It is good if the residuals points follow the dashed diagonal lines. That's what we got here, right? And that is what we get. In our example, all the points fall approximately along this reference line, so we can assume the normality. Next is the homoscedasticity, is homogeneity of variance. The variance of residual is the same for any x values. This is what you get. That will be the homoscedasticity. Okay, you see that? Do you think that they are almost equally spread for each x value? for this value almost equally spread or not? It sounds like yes, right? So we call scale and then location plot or spread location plot used to check the homogeneity of variance of the residuals. Horizontal line with equally spread points is a good indication. Okay. Sometimes if the line shows some pattern like increasing or decreasing pattern, the whole increasing everywhere or decreasing everywhere, then we take log on the residual plots. Okay, so there are other like influential point and then outliers, all those kind of things. We don't check that much, but let me see how it shows. Okay, I have given the description of the influential point there. These are the influential points. So 158, 197 and 203 are basically more influential point there or outlier. Okay, and also 5 is also doing the same thing, that those points are outside those distance I have described here. But the main 3 things I just mentioned should be checked. One is the linearity, homoscedasticity, and then the normality. Those are the main. Okay, so if you want to see all these 3 things, or let me do all these 3 things like this. So you can do 2 times 2, and then you can plot into the shape. See, par mf row and then equals C2 2 is, it will show 2 plot on the top, 2 plot on the bottom. That's what I am going to do here. You see that? Oh, figures 2 margin. So I think it is so because of the smaller region there. That's what it is doing. Let me do that. Okay. So all these 3 plots, the main 3 assumptions are here. But if you want to do all 5 and 5 like that, okay, you can do that too. So 2 times 3, that means 2 rows and 3 columns. Okay, you can do that too. Okay, all right. So another way is you can do par mf row 2 by 2 and then plot linear model. If you do that, so it will basically actually this let me do, you know what, I should clear up here, and then you can do again. Look at this. So it shows residual versus fitted, normal QQ, and scale and location, and residual versus leverage. Basically, this will show you the outliers and the influential point. Okay, scale location, it does the homoscedasticity. Okay, and then you can basically guess from here too, but this is more frequently used for the homoscedasticity. Normality, linearity. Okay, guys, this is what you do. And again, what I have done here is, you see that you see that if you want to go further, more detail, because you see that 58, 76, 197 and 158 were the numbers seen here. Okay, you remove those data and then do the other one. Okay, you can try so many other things here. This is what you do. Okay, you see that whenever you remove those scale and location from the residual versus the leverage plot, you see that the most influential point and then the outliers, you remove that this way. Data faithful minus C, you are removing that. That's what we are doing, minus, and then all the columns are there. Only those rows, those values are removed. Those ranks are removed. Okay, and then if you do that, it improved a little bit, right? Before it was 0.80. How much was that before? Before I think it was 0.81. Now it is 0.82. The RSE, residual standard error, is before it was 49. Now it a little bit improved. It is a little smaller, right? And p-value is already smaller there. So F statistic also changed a little bit. So you can do that. Okay, so in the next video we will discuss about the multiple linear regression. Okay guys, thank you.